Welcome to lesson number 7, the inverse of a relation. So far we've established 3 ways of finding the inverse of a function. Number 1, we can reverse the coordinates in a set of pairs. We can reflect the graph in the line y equals x, and we can interchange x and y in the equation and solve it in terms of y. Now, some relations are functions, others aren't, and it goes for the same with their inverses. So in this lesson, we're going to be looking at inverse of a relation where I have something like x minus 3 squared plus y squared is equal to 9. Now, the first thing we want to do is describe how we could use our graph to draw the graph of the inverse of a relation. So we're told that I have a center at 3 and 0, and at 3 and 0, and it has a radius of 3. So I have a point there, point there, point here, and here. And we're also told it's a circle, so then we could draw our circle. Now, we could reflect this in our y equals x. And so y equals x is the line that runs through right here, runs through my origin diagonally. Now, all these points are going to be inverted across this line or reflected across this line. And so when I have a point here at 6 and 0, it's going to then go up to 0 and 6. When I have a point at the origin at 0 and 0, that's where it's going to stay. When I have a point that's at my center of my circle at 3 and 0, that's going to be reflected to 0 and 3. And then we could build our graph around those points. And so my new graph is going to look something like this. And what we did was we just reflected this. So reflect in y equals x. And so we sketched our graph, part B is fulfilled, and describe how to use the equation of a relation to determine the equation of the inverse of the relation. And so all we need to do is that third method for solving inverse functions and to interchange x and y. So wherever I had a y value, it's now an x value. The equation is going to look something like this. So this is my original equation, but if I interchange my values, this is now going to look like this: y minus 3 squared plus x squared equals 9. And then if I were to rearrange this equation, then well, actually, that's all. I could leave it like this, unless you want to put x squared first and then y squared afterwards. But this is good. Now, write the equation of the inverse in D by solving for y, and then verify the sketch in B on a graphing calculator. So now we want to take this equation and we want to solve it in terms of y below. And so I'm just going to go from here. The first thing I'm going to do is I'm going to subtract x squared to this side of my expression. And so if I subtract x squared over here, then what I'm going to be left with is y minus 3 squared is equal to 9 minus x squared. The second thing I'm going to do is I'm going to take the square root of both sides. If I take the square root of both sides, I get y minus 3 is equal to plus and minus the square root of 9 minus x squared. And last, I'm going to add 3 to both sides, leave me with y is equal to 3 plus and minus the square root of 9 minus x squared. Now, let's graph this and see what it looks like. So I'm going to have two lines I'm actually graphing. I got 3 plus the square root of 9 minus x squared. And I have 3 minus the square root of 9 minus x squared. So there's the top portion of my graph, and then there's the bottom portion of my graph. It doesn't really look like a circle here. We would have to adjust our window settings, probably my Y window settings. And now stating the domain and range of our graph. So using interval notation, we want to state the domain and range of the relation of the domain and range of the inverse. So let's see my relation. So relation. Using interval notation, I'm going to use set notation here. It's going to take a little less space. So if I'm talking about the domain here with set notation, my x values extend to 3, and they are also inclusive of 3, or sorry, of 0. And then on the far end, they're inclusive of positive 6. And my range is going to be inclusive of negative 3 and positive 3 up here. Now with my inverse, not my function, my inverse, it was reversed. So my domain, now if you look at the domain is at negative 3 and positive 3. And my range is at 0 to positive 6. So I'll just do this one here. If I'm looking for, if I have f of x and that's equal to x cubed plus 4, the inverse, I would first substitute f of x with y, and I would just label it x cubed plus 4. And then the next thing I would do is I would interchange my x and y variables. So that's going to be x is equal to y cubed plus 4. And then I need to subtract 4 from each side. So that's going to be x subtract 4 is equal to y cubed. And then if I take the cube root of both sides, and I'm just going to put my y here, I'm going to get cube root of x minus 4. The last thing to write this in inverse function notation is to say f of negative 1 of x is equal to cube root x minus 4. In class example number 3, I have the function x squared minus 4, and I want to graph y is equal to f of x on the grid provided, and then I want to state the domain and range. And so x squared, it's going to look something like this, and then I'm going to have a point here and here, so it's going to look something like that, and it's going to increase upwards. So remember, when you're writing your standard parabolas, if the only transformation on this is it moves down the y-axis negative 4 spaces from my origin, then you can write it like that. Now I want to, if I graph f of x, I now want to state the domain and range. Well, the domain, x is an element of real numbers, there's no restrictions. For the range, y has to be greater than or equal to negative 4, and y is still an element of real numbers. Now I want to determine x of f, x is equal to f of y, and then solve for y. So the way I'm going to approach this problem is I'm going to set up my equation by interchanging my x and y values. And so y is equal to x squared minus 4 is my original expression, and then I'm going to interchange my values. X is equal to y squared minus 4. Now all I got to do is add 4 to this side. I get x plus 4 is equal to y squared, and y would then equal plus and minus square root of x plus 4. Now what this would look like is we would plot our first point here, and then my positive radical function, or relation in this case, is going to go up like this, and my negative radical expression is going to go down the opposite side like that. And so again, we're just reflecting an x is equal to y, or y is equal to x. Now the domain, my value of x right here, x has to be greater than or equal to negative 4, such that x is an element of real numbers, because there's no values of x below here. But my range is y is an element of real numbers. So any value of y is gonna work here. However, is the inverse of f a function? No, it's not, because it doesn't fulfill the vertical line test, and there's multiple y values for every x value here. So no, the inverse is not a function. So in this example, Don incorrectly determines the inverse of the function. So here's my function divided by y is equal to the square root of x minus 3 to be the equation y is equal to x squared plus 3. He then graphed the inverse of the function and obtained a parabola. So explain why Don's equation of the inverse is not complete and why the graph of the correct inverse is not a parabola. So here's my my original function, y is equal to x minus 3, square root of x minus 3. If I change those values around, y and minus 3, then I'm going to square both sides. It's going to be x squared is equal to y minus 3. And then I'm going to obtain y is equal to x squared plus 3. And that's what Don got. He got this expression. Now the only thing is, with his original expression, y is equal to square root of x minus 3, because this is only positive, it's only a positive radical function, it wasn't plus or minus. And that's what the problem is here, is this original expression isn't plus or minus, so this is the only thing that he's taking the inverse of. So when we actually take the inverse of this expression, which would translate to this, we would actually have to just reflect it up my y-axis, because we are not including the negative values on the square here. And so even though this is correct, the graph should only include the positive radical function. And that's included, and the graph should also only include the positive, or the inverse of this positive function. Next, I'm going to take a function, and I'm going to form a composite function with its inverse. So determine f of the inverse of f of x and the inverse of f of x for class example number 2, where f of x is equal to 2x minus 3. And what do you notice? So first of all, f of x is equal to 2x minus 3. And if we go back to the class example number 2, the inverse, we actually could do that one. But anyways, the inverse, if we do this quickly here, the f of negative 1 of x would be, we'd have to add this to the other side and then divide it by 2. So we would have 1/2 x plus 3 over 2. So that's the inverse that we're looking at. Now, if I'm doing the f of the inverse of x, then this is what this is going to look like. So we have f of negative 1 of x is equal to, so first of all, this is what's going inside our function, is going to be 1/2 x plus 3 over 2. And around this, we're putting 2, and that's the x, taking the place of x. And it's going to look something like this. Now, if I distribute this 2 inside my brackets, I'm going to end up with x plus 3, right? Because 2 times 1 is 2 over 2. That's going to just be 1x plus 2 times 3 halves is going to be 6 halves, which is just going to equal 3, and then we subtract 3, so this is equal to x. If I look at the other function, so f of inverse of f of x. This is going to look like this. So 2x plus 3, and I'm multiplying this by 1/2 plus 3 halves. And so 1/2, if I distribute that inside my brackets, we're going to get x again minus 1/2 times 3 is 3 halves plus 3 halves. This is also equal to x when we simplify. So both f of negative 1 of x and f of negative 1 of f of x are equal to x.